And I'm Kate, and we are going to show you why we should have our insurance prices lower.
First, we're going to talk about how following distance, braking distance, and the total stopping distance all connect.
Following distance is the distance between your car and the car in front of you. For example, Tia is car A, and I am car B, and the distance between us is our following distance. The following distance needs to be greater if you are traveling faster, because you are going to travel further before you react to the car stopping. You can calculate the distance traveled during reaction time using the equation distance equals average velocity times the reaction time. For example, if we are traveling on 31, we're going 40 miles per hour. So our feet would be 58.67 feet per second, and then our reaction time is 0.19. So that would equal 11.14.
Braking distance is the distance that it takes for your vehicle to come to stop when you have a flight break.
Braking distance causes you to have a negative acceleration. Acceleration is the change in velocity per unit of time and equality. So it is a change in speed or direction. All of these graphs show negative acceleration, and then this graph shows the relationship between braking distance to the initial speed. So like if you're at a faster speed, then your braking distance would be higher than if you're going at a slower speed, and your braking distance will be lower. And then you can find acceleration using this equation, which is acceleration equals the change in velocity over the change in time. The faster the vehicle is moving, the greater the braking distance will be. You can calculate this using the equation Vf squared equals 2ab plus the initial velocity squared. So the final velocity squared equals 2 times the acceleration times the distance plus the initial velocity squared. If the velocity doubles, then the braking distance quadruples. And if the velocity triples, the braking distance is 9 times as great. Also, the total stopping distance is the distance time you react to the time your car comes to a complete stop. So, for example, if the car in front of us were to just stop, then it would be the time that it takes for Tia to react to the car stopping, and then for her car to come to a complete stop. Next, we're going to explain what yellow light analysis is. This helps us to avoid accidents from running red lights and getting in trouble with the law.
The go zone is the section of the intersection where vehicles can safely make it through the light. The go zone increases as the yellow light time increases and when your speed increases. The go zone decreases when the width of the intersection increases.
The go zone can be calculated using this equation. The go zone equals the velocity times the yellow light time minus the width. We currently cannot go through a yellow light because none of these lights are changing to yellow, so you get the point that if the light is yellow and you have enough distance to go through the light based on your speed and the width of the intersection, then you can go. But if you do not have enough time, then you need to stop in order to be safe and not run a red light. We're coming to this light, and we are obviously at a stop zone because we are so far away from the yellow light that there was no way for us to go. And it did not stay yellow for that long, so if we would have went, then we would have got stuck at the red light and probably caused an accident. The stop zone is the velocity times the reaction time plus velocity squared over 2a. The overlap zone is where a vehicle may either stop or go through the light and be safe.
This is a light.
While the dilemma zone is when an intersection is poorly designed, where no matter what the vehicle does, they are in a bad situation, but this rarely happens. It is good to know this to be prepared for a poorly made lights and try to, we are going to explain the speed, friction, and radius of a curve when turning and the relationship between them.
Now, with centrifugal force, to keep an object moving, the friction can be less if the radius is greater, and you can go at a higher speed without, dying.
But there is a maximum friction force when driving in a circle that the road's surface has. So if your speed is too great, then the curve is, or if the curve is too sharp, you will not be able to stay on the road.
And right now, on this roundabout, I can't go too quick because of how small the radius is. I'd say it's about, probably 50 feet.
But if the roundabout was bigger, then we'd be able to go at a higher speed.
Because currently, it is you!
The max friction force can be found when you take velocity squared over the radius. And then this is a diagram explaining what we just said pretty much, because if you have a higher velocity, then you can go, it's the radial, the tighter the curve, then the slower you are able to go. So if the radial distance is lower, then you're not able to go as much as a fast speed.
No.
Give it time. Give it time. The video's not over now, so.
All right. I have 6:48.